Hey, good morning. We have homework due on Friday, 2 days from now. And my first question is, are there any questions about the homework? Anybody stuck on anything? Anybody need some clarification? Okay, you got something. All right.
So it says on 6.35 to get a constant, a value for a constant.
Yeah, the diffusion constant?
Oh, the diffusion constant?
Let's see. Find the diffusion constant in terms of the axon parameters.
Yeah,
So,
I got stuck there.
Okay, so what did you get for W? What equation?
Well, I think it's wrong, but it is, what is this matter declared? Lambda squared, and then the partial derivative of W in terms of x squared.
So this.
Yeah, and then plus the partial derivative of W in terms of t. I don't know if that's right, but I caught that.
Okay, and that's all equal to 0, or?
That's equal to W x t.
Okay, you're on the right track, but what you should end up getting for W is something that looks like the diffusion equation. So let's see if we can just kind of get you started here. On problem 35, you have the cable equation, delta squared. Let me write down what it has in the problem. Minus V minus V minus tau dV dt equal to 0. And then you assume that V is equal to W e to the minus t over tau. Okay, now, so what did you do? You plugged it in? Okay. So we plug this in. That this doesn't have any x. So it just becomes lambda squared e to the minus t over tau, and you have two derivatives of W. Okay. That's kind of similar to what you had. And this is just minus V, which is W, e to the minus t over tau. And now how about this one? What did you get for this term?
I got e to the negative t over tau, all over tau. So that over of tau.
Okay.
And then the partial derivative of W in terms of t.
So like this?
Yeah.
Okay, and that was a minus or a plus sign out front?
There was a minus sign.
Okay, so that, when you put this in for V, that term is, I'm not quite sure why it's 1 over tau. See, what you have here is you have a product rule. You have W, which depends on time. You have exponential, which depends on time. So you'll have to use you're really going to need to get two terms. One's going to kind of look like your exponential over tau, and one is going to look like your dW dt, but it's going to be two terms.
Okay, I see.
All right? And then you're going to see some nice cancellation, and you're going to end up with something that looks a lot like the diffusion equation for W. And then you have to identify what the diffusion constant is, because you know the diffusion equation looks like this. For just any old variable, the diffusion equation is that thing. So you'll cancel out the terms. You'll find that W obeys the diffusion equation, and then you'll move everything over into a constant, and then you'll say, well, those constants all together make up the diffusion constant D. So that's the key here, I think, is to realize that when you do this term, you have a product rule, because W depends on both x and t, so it depends on time, and this exponential depends on time. All right? Other questions on homework number 6? Yeah.
Just real quick, on number 1, it says
Yes.
Fiber. And then it says with the larger diameter fiber that the speed goes to 85 meters per second. Are we just supposed to assume that the speeds are proportionate to the radius of the fibers?
No, you're just supposed to use the speeds given, because we're going to see later on today, myelinated fibers are proportional to the radius. Unmyelinated fibers are goes to square root of the radius, and so you can't really make a simple comparison between unmyelinated and myelinated. So just take the given speeds as if you didn't even know the radius of the axon, and you have to get the distance and the speed, and you can calculate the time. Okay. Anything else on the homework? All right. If you have questions, contact me. I think we already talked about all these problems, so there's nothing else I really have to offer right now. Okay, the next thing I wanted to do is clear up one point from the end of last class where I screwed up a factor of 2. I just wanted to show you how to do it correctly. We were looking at a nerve axon, and we were injecting some current in at x equals to 0. And we were injecting in I0. And the point is, half of that current will come out and will go this way. So you have I0 over 2 going to the right, and I0 over 2 going to the left. And we know the current density is equal to minus sigma times dV dx. So what we wanted to do is we wanted to relate I0 to the voltage right here at the nerve. I'm not going to go over this whole calculation, but that says that the current going down to the right is I0 over 2. And that's got to be equal to the current going to the right from our equation, which would be, this is a current density, so you have to multiply by pi a squared. And you're going to get a minus sign here, and you're going to multiply by a sigma. And then if you took that expression for dV dx and you evaluated it, you're going to get, and it's evaluated at x equals to 0, you're going to get V0 over lambda. That part you're going to have to just verify from your notes. But you end up, but the factor of 2 is right here, and you also get a minus sign when you evaluate dV dx because it's going down. So the 2 minus signs cancel. And you end up with this expression. And then if you move everything over to the other side, you'll get lambda over 2 pi a squared sigma equals V0. This looks just like Ohm's law. V equals IR. This thing is the input resistance. And I had the factor of 2 in the wrong spot last class. I believe it's because I multiplied instead of divided by 2 over here. So that's one way you can calculate sort of the overall resistance. So if you stick an electrode into the fiber and you want to get a certain amount of voltage right at the underneath the electrode, this is the sort of resistance that the fiber represents. So that hopefully clarifies that point right at the end of last class. Okay, any questions before we go on to some new material? Today's going to be really the last day we talk about Chapter 6. And then today is Wednesday, Friday, and Monday we'll review for the exam. We have those practice exams, and then the exam is a week from today. Yes?
That term is R input, not 1 over R input? Or is it?
This would be written as V equals I R.
Okay.
So this whole thing in the parentheses would then be R input. Just from Ohm's law. All right. Then let us go on and start the final material. We're going to talk about how action potentials propagate along nerve axons today. So I'm going to erase all this, and we will move on. Okay, first thing I'm going to do is I'm going to write down our 3 basic equations that we derived yesterday that went in to our calculation of the cable equation. One I just erased. The intracellular current density is minus sigma dV dx. Then we got an equation from the continuity. That is, current coming in is equal to current going out of a little chunk of axon. And we got minus A, the radius, over 2, dji dx equals jm. So let's just remember what all these symbols are. Sigma is the conductivity of the cytoplasm, the intracellular space. A is the radius. Ji is the current density going down the axon. Jm is the current density coming back out through the membrane. And we also had Jm is equal to C, a capacitive term, plus Vg, capital G, is a membrane conductance. And we assumed G had no gates opening and closing, was just a fixed resistor or conductor. This is the assumption that we're going to get rid of today. So what we're going to do is we're going to do exactly what we did last class when we derived the cable equation. We start with this equation, and for Ji, we'll put in that. And for Jm, instead of putting in this, we'll put in the Hodgkin-Huxley model for Jm, which is this, except it divides this current into 3 terms with all the gates. So what we end up with when you do that, and we're going to, let's see, we get a sigma, an A over 2, and the minus signs go away. So you get a sigma A over 2. Here you have a derivative of a derivative. So we get d squared v dx squared equals, and then we get the Jm, which is d, Hodgkin-Huxley said there's a capacitive term, plus a sodium term, m cubed h, v minus v, v and a, plus gk, n to the 4th, v minus vk, plus g leak, v minus v leak. And there you have it, the entire equation governing how action potentials propagate along nerves. You also have your 3 equations for M, H, and N, just like we had in the Hodgkin-Huxley model. Now, this is a nonlinear differential equation. It is nonlinear in part because of the m cubed and n to the 4th, but also because those parameters in the equations for m, n, and h, the lambdas and alphas and betas, in other words, the m infinity and tau m's, dependent on voltage in a very nonlinear way. So it's nonlinear and it's a partial differential equation. Looks like the diffusion equation from these first 2 terms. So what you get is you get behavior that looks like diffusion, but it also looks like this action potentials. So a nonlinear partial differential equation, which we're not going to solve ourselves. But I want to show you qualitatively how this works. So the key things to remember are you have diffusion, plus you have a reaction. So sometimes these are called reaction diffusion systems. The reaction is the firing of the action potential if the voltage raises up enough. So let us draw just some pictures. See if we can understand this in pictures. Here's your axon initially. And initially, you've got minus signs inside and plus signs outside. It's at rest. It'll sit here at rest for a long time until you do something. So let's put an electrode in here and we will inject some current, to depolarize the nerve. Remember when we calculated how the voltage behaves along an axon? It spreads out, but only over a distance lambda. So what's going to happen is over a distance lambda, you're going to begin to get positive charge here. And the outside a distance, it won't have any effect. So you'll have negative charge. So here's your electrode. You injected positive current. You injected positive charge. What happens next? Well, this equation tells us that there's a voltage gradient you're going to have a current density. There's a voltage gradient here because this is at positive potentials, positive charge. Here it's at negative charge, so there's definitely a voltage gradient coming down this direction. Current's going to be going down the axon here, and it's going to be going down the axon here. But this equation says if the current changes with x, so here it's going down the axon, and here it's 0 because there's no voltage gradient. If it's going down the axon, it's got to go up through the membrane. So it's going to go out through the membrane here. And what it's doing as it goes out through the membrane is it's actually taking that positive charge and it's putting it onto the membrane. It's diffusing down the axon. In other words, the positive charge, this current carries positive charge. When it gets to the membrane, it plasters positive charge on the inside, and that removes negative charge to flow on the outside. So it crosses the membrane just through a term like this. And then on the outside, it's going to go out, and here, right underneath the electrode, this is positive charge. That means the voltage raised up. So let's say it raised 10 or 20 millivolts. What's going to happen? If you take a nerve and you raise the voltage 10 or 20 millivolts,
It fires.
it's going to fire. You're going to have the M open, and the M open is going to let sodium in, so you have sodium coming in here where during the action potential. Sodium come rushing in, firing action potential. So this is the middle of the action potential right here, and these are the currents that are flowing along. And it all follows from these basic equations. What happens next? Okay, well,
Bless you.
the action potential, here's the electrode, it's now turned off, so we turn off the stimulus. The action potential, after it fires an action potential, eventually recovers. Eventually the sodium channel turns off because H closes. Potassium channel opens even more, so you get potassium current going out. Here, this voltage here on this membrane was raised by this current. It raised the voltage until the voltage increases enough that sodium rushes in and you start an action potential here and here. Now you have this area back to negative because it's back to rest. This area becomes positive because of the action potential, which causes a voltage gradient. It causes currents to go down like this, back the other direction. And you also have negative current out here because it's many length constants away. But now you have positive charge here, negative charge here. You get a current going down there. No current here because your no voltage gradient. So this equation says if the current changes, it had to go up through the membrane. And this is where an action potential flows, so it's sodium coming in. So you have these current loops that look like this. Here you have an action potential. Here you have an action potential. Here you've recovered, and here it's still at rest. What happens a little later time? Do this one more time. Okay, here you've recovered back to rest. Now at this point it recovers. So you got a bunch of negative signs there. Way out here it's still at rest. But this current here is depolarizing the membrane. That's creating positive charge. If it depolarizes enough, the M sodium gate opens up and in comes an action potential. Action potential right here. The action potential will bring its positive charge. You have a voltage gradient here going that way and here going that way. And it will come out here and start charging the membrane. Here it comes out as potassium current. And the same thing happens over here. You have an action potential starts here, so it becomes positive inside as the sodium rushes in. Now you have a voltage gradient. A voltage gradient comes out here. This is what happens when this action potential finished. H gate closed and it's potassium current. Over here it's capacitive charging the capacitor, and then it closes its circuits. So what you have is this distribution of current is propagating that down along the axon. If you go down further, it just propagates out further. This is the way action potentials propagate along nerve axons. It's the way we send signals from our brain to our muscles and back, is firing action potentials that propagate along like this. All right, so there's another interesting thing. These a little bit like waves of water or electromagnetic waves, but they're also a little bit different. For instance, if you took two water waves and you fire them at each other, they just pass through each other and they come out the other side. Same with light. Take two lasers and fire them at each other, the light will come in and pass through each other and come back out. If you took two action potentials, say this one and another one you started out here, and they fire at each other, then they're eventually going to reach and they're going to have to pass through each other's refractory periods, which they can't do. So they annihilate and they just stop and you end up with nothing. So they're a little bit different in their usual ways. They're non-linear waves in that when they fire and they hit each other, they annihilate and everything stops. So it's a little bit different properties than a lot of waves you're used to. They also will tend to fire. This will propagate along with a uniform amplitude. The action potential always goes up to about the sodium Nernst potential. And it's as if it keeps getting energy as it propagates along. It doesn't decay as it propagates along, because every spot is sort of a recharger to recharge and put that energy in, allowing it to go up to the sodium Nernst potential. So there's lots of different ways to think about this, but you get propagation. Another analogy, there's a couple interesting analogies, is like a fuse. If you light a fuse, if you watch the cartoons, there's a big bomb and the fuse is coming off, and you light the end of the fuse. Okay, the fuse starts to burn and it gets hot. The heat spreads out pretty much by diffusion until it lights up the next part of the fuse, and that fuse burns. And then that will spread out the heat until down here it'll fire again, and the fuse then burns down along until it gets to the bomb. Kaboom. If you had already burnt a spot, you couldn't pass through. That's like a refractory tissue. If you started the fuse at two spots and they burn towards each other, they poop out. The same thing goes with forest fires. If you started a forest fire and it was propagating along, the heat would cause the other trees downstream to burn, and they would then begin to burn, and it would be a source of fuel for the fire. It would burn, it would heat up, and it propagates along. If you had two forest fires coming at each other, then bang, they annihilate because there's no fuel left. So you get all these kind of interesting analogies. Okay, how fast does it go? Well, it's hard to calculate exactly, but we can do an approximation. How far is does the current spread? Well, how far would it spread if it was sort of steady state? Maybe a length constant. Something on the order of the length constant we calculated last class. Yeah, that's a rough approximation, but it shouldn't be orders of magnitude difference in that. And how long does it take to spread that distance? Well, nerves operate on the order of tau, a time constant. So you expect the speed of this propagation to be something on the order of a length constant over a time constant. And we found the length constant was about 1 millimeter, and the time constant was about 1 millisecond. So you get 1 meter per second. And that's how fast a typical nerve would spread. It turns out lambda depended on the axon radius. So if you made the axon radius bigger, the speed would get faster. It's exactly what happened in the squid axon. The squid axon needed a very fast response to do its escape reflex, and the only way it could make it faster action potential was to increase its lambda, so it increased its radius. All right, now if you look in problem 1 in the homework and you use action potential of about this speed, it's kind of slow. It doesn't allow you to do fancy things like play the piano. So we need a way to speed it up. So how are we going to speed things up? You got two options. You can do what the squid did. You can make your axons bigger. And that works great. I mean, the squid proved it. But if we have a millimeter diameter axons, we can't have many before we fill up our whole arm with axons, and she can't run a hand to do the things we want to do with just a few axons. This is where problem 2 is coming in the homework. you can't have big axons and have a lot of them. There's just not space. So we need another way to speed things up. And the other way is we undergo myelination. So this brings us to the topic of myelinated nerve axons. So before I start talking about those, let me ask if you've got any questions about this sort of discussion of propagation. Okay, then let us look at myelinated nerves. Get rid of all this. Okay, so here's the way myelination works. And by the way, myelination is in mammals, it's in birds, it's even in some amphibians. I don't remember if it's in reptiles, but you get down to really lower organisms like the squid, and they haven't developed myelination. It's something that came along, evolutionarily came along a little later. So you take your nerve axon, and the trick you use is you're going to wrap it up in fat. So basically a layer of what's called myelin, fancy word in our case, just a layer of fat with no ion channel. So it basically is an insulator. But if you totally insulated the whole nerve, the nerve wouldn't work anymore. But what you do is you leave a few spots. So you wrap this part with myelin. Then you wrap this part with myelin. So it begins to look something like this. Now these spots are called nodes of Ranvier. And that's where you put all the sodium and potassium channels. So what's going to happen to a rough approximation is instead of propagating uniformly, it's going to fire an action potential here, and then it's going to propagate that action potential down, but it's going to be very effective of propagating through this area because it's insulated so that it doesn't lose any current to the outside. So basically, it propagates very quickly down to the next spot, and then it'll fire an action potential. And then this spot will fire an action potential. So it works very similar to what our previous picture was, except it sort of fires from spot to spot. Something called saltatory conduction. I wanted to show you what this looks like from a side view. So say we take, here's our nerve axon, we're looking now down from the side view. So here's the axon itself. And what the myelin is it just a bunch of fat layers like membranes, basically, wrapped around here in a spiral pattern around and around and around like this. Okay, that's what myelin is. That's how you make it. You just wrap up that nerve. So, let's think about the capacitance for a minute. The effective capacitance, that is the capacitance of the entire myelin layer, is basically, well, this is a bunch of capacitors, they're cell membranes, and they're all in series. Now, resistors, when you add them in series, you just get more and more resistance. But capacitors, when you add them in series, it's like resistors in parallel. So you end up getting the capacitance of the membrane divided by n, the number of layers. So you essentially get a smaller and smaller capacitance as you wrap more and more layers. As you reduce the capacitance, that means the time constant, or at least the effective time constant, is smaller. Okay, so you make n bigger. I'll make capacitance smaller. And time constant is basically an RCE, so it makes the time constant smaller. And if you make the time constant smaller, that was in the denominator of the speed, so the speed gets bigger. So essentially, you are tricking the nerve by making its effective capacitance really small. Allows you to make its speed really big. So it's faster, it tends to hop from one node to the next, and you have a way to speed up the action potential. And in fact, it works fairly well, and we can get speeds like, if you look in your homework problem number 1, if you get speeds that are up to like 85, even 100 meters per second. We also tend to make the nerves a little bit bigger. It helps a little bit because the length constant does increase the square root of lambda in this case. So we tend to make the nerves a little bit bigger, and we use myelination, and we can get a speed up of almost a factor of 100 over what it would be if it was just a bare nerve axon. And it allows us to have lots of fast fibers, just what we need to be active human beings. So that's a little bit of how myelination works. Now, what I want to do next is I want to do a problem not in your homework. 69. So problem 6.69. Okay, here's what it says. Let's suppose that this is your radius of the main axon. And this is the thickness of the myelin, B. And the total outer radius is going to be D, and D is just A plus B. Okay, now suppose you were trying to design an animal. You want to have a lot of axons, so you can't make D arbitrarily large. So let's say D is fixed. Let's say that you have a certain amount of space, you want a certain number of axons, so you can't go any bigger in D. So D is fixed, but what we do have some control over is A and B. Let's just talk about A, because once you specify A, you'll specify B. So the question is, for a given D, what do you make for A? Do you want to do this? Here's one option. You can make A real small. So you have an axon, like tiny little axon and tons of myelin. And you might think that'd be great. That's going to be a lot of layers. It's going to make my capacitance go down. Problem is, it makes the resistance along the axon really big because that resistance goes up. So even though you get a lot of myelination, you pay the price, and then it can't go very far because the axon resistance is so big. So let's go to the other route. Let's go a real thin layer of myelin. Well, then you might as well, why bother? Because if this myelin is real thin, you'll have hardly any values of N. You might as well just use a big unmyelinated axon. So it turns out that the best compromise is somewhere in between. And this problem has us calculate what that best compromise is. What's the best value of A given a fixed D? So let us see how this works. And there's going to be one thing that's sort of a cheat here. Lambda, we found, was A sigma over 2, and I'll put G, I'm going to call it G effective. That's what we found for a nerve axon, the space constant. G effective means the membrane resistance plus the resistance of all this myelin. And you want this to be really big. But you can calculate what the G effective is, and this is the part where I'm not going to do the whole calculation. What I'd like to do at this point is stop and do a calculation based on Gauss's law to try to calculate what the net resistance is of a cylinder inside a cylinder, but we don't have time for that. So I'll just say, I'm just going to be a proportionality sign. You're going to get 1 over A log D over A. That is going to be the proportional to the effective conductance. So you have to just trust me on that. So what we have then is we have lambda is equal to, well, there's going to be some constant proportionality. It's going to involve the proportionality constant here plus the sigma and the 2. I'm just going to lump all those into a constant k. How does it depend on A is what's important. Because it's got an A here, and it's got another A here, which is in the denominator, so you're going to get A squared log V over A, and it's inside the square root. Or, if you prefer, well, that's fine. Okay. So now we have an expression. And in fact, we can actually write that as, I hate square roots. Lambda squared is a constant squared, A squared log V over A. What we want to do is we want to try to make the space constant as large as possible. And if we make the space constant large, we make the space constant squared large. So we're basically, this is an optimization problem. We want to make lambda as big as possible. Now let's look at our choices. We could have A really small, go to 0. And you might think that'd be great, because A is 0 down inside here, so you get log of infinity, which is infinity. But you got this A squared out here, which goes to 0. And it turns out if you do a limiting procedure, this goes to 0 a lot faster than this goes to infinity. So you'd end up getting 0. So if we made A 0, our space constant is going to be essentially 0 because of the huge resistance going down the axon. Okay, let's try the other case. Let's try to make A equal to D. Make it a real thin layer. As A equals to D, you get D over D, which is 1, and the log of 1 is 0. So you get 0. This thing is no special value, it's just D. So you get 0 for the length constant. So what it says is either of these two cases give us 0. There's going to be some plot of lambda squared versus A from 0 to D. And we know it's going to be 0 here and it's going to be 0 here. But it's not going to be 0 everywhere. It's got some funny shape. And we want to find where it's biggest. How do you find where it's biggest? Well, head calculus. What do you do if you want to maximize that function? Set the derivative to 0. The derivative is the slope of this curve. It's going to be 0 at the maximum. Okay, you can worry about whether it's a minimum or some kind of weird point, but it's pretty clear that this is going to be our maximum. And this could have some funny shape, but it doesn't. And if you plotted it, you'd find it goes up to a unique maximum. So let us do d lambda squared. And now this is a funny thing because we are varying A, dA. Okay, and we're going to set that to 0. All right, so here's our constant k squared, which is going to go away because it's equal to 0. We have an A here and an A here. So what are we going to do? We got a product rule. We have a product rule, so first let's take the derivative of this times this. Derivative of A squared is just 2A. Log d over A plus this A squared times the derivative of this. This one's a little tricky. The derivative of log of d over A. Well, the derivative of log is just 1 over the function. So you get 1 over d over A. But then you have to take, by the chain rule, the derivative of the inside, or the derivative of d over A. So I'm doing the chain rule here. I'm taking, basically I'm saying du, let's see, d log u dx is going to be equal 1 over u du dx. That's the rule for logarithms. So I've got, here's my 1 over u, and then du dx is going to be d times, that's a to the minus 1, so it's going to be a minus d over a squared. That's just like asking what's the derivative of 1 over a. It's minus 1 over a squared. So we're almost there. Trust me. Okay, the case comes out because this is 0, so I just divide through by the k squared. Here's your 2a log d over a, and there you got a minus sign, and you have a d here, cancels that d, and a squared cancels that a squared, and this a comes up. You get an equation that looks like this. It's all equal to 0, and the a's are in both of these terms, so I can divide those out, and I'll get, let's bring this to the other side, I'll get 1 equals 2 log d over a. So I get a half equals log d over a. So I get e to the 1/2 equals d over a. So I get a is equal to d over e to the 1/2, which, if you do the calculation, is 0.61 d. So what did we do? We figured out the optimum value of the inner radius. We found the value here is 0.61 times d, not too different than what I drew. And what's that mean? That means if here's your axon, fixed D, here's its center, you go out to the center, here's a half, here's about 6'1". All myelinated nerve axons look about like this. Here's all this myelin, and there's the axon, and that's the best way to divide up axoplasm and myelin to get the fastest nerve axon. So we've kind of used mathematics to discover how to make the best nerve axon. If you look at myelinated nerves, they all look like this. Doesn't matter what their D is. Once you specify D, they all have the same A, about 0.61 times D. So under a microscope, you take a cross-section of a nerve and you look at the axons. All the myelinated axons look like that. So we figured out how animals have built their nervous system. Yes?
Why at D would, when A equals D, would lambda equal 0? I understand like mathematically, but wouldn't that just be like an unmyelinated?
That would be, well, with A equals D, why would lambda equal 0? I guess what we're doing is we're sort of, technically it would, because there really is a resistance associated with the nerve membrane. But if you sort of ignore that compared to the myelin, then you're essentially having 0 resistance for the myelin. You're getting 0 membrane resistance in that limit. Like I said, it's sort of an approximation because there is a fixed membrane resistance that you wouldn't get rid of. But to ignore that fixed membrane resistance, your myelin resistance goes down to 0, and that's why you get to 0. So technically, it's probably just a little different than 0, but it's still going to have that general shape. Good question. Anything else? Okay. There's another thing that nerves do. Let's see how we do here. So, myelinated nerves. And they tend to be built like this. Here is a nerve from a kid. And it's got myelin like this. As the child grows, the nerves gets bigger. And what happens is the myelin, well, maybe not the kid example, but here's the myelin for a nerve. A bigger nerve is going to have myelin, thicker myelin, but it's also going to be longer myelin between the nodes. Okay, that in some sense is just the way. I don't have a real good explanation for why nerves develop in that way, but larger nerves tend to have larger distances between the nodes. And that lets them get even faster. So the bigger it gets, the distance between the node gets bigger. You want that distance as large as possible without actually having a failure because the nerve won't propagate. So you get even bigger, faster nerves. And this is why, in the end, unmyelinated nerves have the speed proportional to the square root of A. That is here. Unmyelinated nerve, this is just a fixed conductance. You go a square root of A. But myelinated nerves, the speed goes proportional to A itself. It's in part because of this, and it's in part because of this different step size, the way the nerves are arranged. So you end up getting a myelinase increase with A. So, what does that imply? Let's see if we can learn a little bit more how nerves are designed. I didn't really justify this too rigorously, but let's take that as a given fact. And let's plot speed versus A. Myelinated axons, they're proportional. Speed's proportional to A. So for a myelinated axon, they just go up like this. Unmyelinated axon, it goes to square root of A. So square root of A, have you ever plotted square root of A? It starts at 0, and it goes up really fast, but then it turns over, and it continues up, but much more slowly. So unmyelinated axon. So here's the funny thing. If your axons are small enough, it actually doesn't help to myelinate the axons. You should leave them unmyelinated. But if the axons are bigger, then it pays. And it pays a lot as you go out to really big axons. So there's a crossover point right here. And this crossover point in the nervous system is approximately a 1 micron radius axon. So what you find is that if you looked at a nerve, this is an entire nerve, like the median nerve in your arm, and the larger axons are myelinated. So let's see if I can draw this right. This is kind of our typical myelinated axon, a whole bunch of them. And then in between are a bunch of real tiny axons, and these tend to be unmyelinated axons. These big axons are your big motor axons that you want to control your muscles. You want to be able to do that fast. So they're myelinated, they're big, you can get good control. These smaller axons are like a pain receptor. You know, you need to know that something hurts, but you don't need to know immediately. So you cut your finger, and maybe a second or two later you say, ouch. It took a while for that signal to get back to your brain. It's not essential that be immediate. So you can get away with using, or other receptors like we can tell sort of where our muscles are in where our hand is, because there's sensors that sense sort of the position of our hand relative to the other muscles in our body. But that doesn't have to be fast. You can get away with slow response. So you can get away with slow response. You can use really small axons. They're slow, but you have a whole lot of them. And you want fast response, you put in some of these big myelinated axons. And the crossover is about a micron. And if you look at nerves, you'll find that roughly a crossover of about a micron between the myelinated and unmyelinated nerves. So what our bodies consist of is a bunch of nerves, thousands of fibers, because this is like 4 millimeters, and these are like maybe 10 microns. So there's thousands of them. And the big ones are myelinated, the small ones are unmyelinated, and that's the way the nervous system works. Note that all these axons can propagate in either direction. When we drew that picture, we had an action potential going down this way and down that way. Now, so all your axons can go either direction. Now, in most cases, if you have a big motor axon, you're sending signals from your brain down to your muscle. The only reason it's always firing in that direction is because the action potentials start up here, and then they travel down this way. If you somehow stimulate them down here, they'll come back the other direction on that same nerve axon. And same thing with sensory signals. The pain receptor here on your finger, normally your finger gets cut, it sends a signal up to your brain, but if you'd stimulated it, you could send the signal back down the other way. They all work either direction. And that is the end of chapter 6. So that's all the new material for the exam. Any last questions about nerves and how they work? Yes?
Will we ever encounter a nerve that varies in its diameter over its length?
Good question. I'm sure they do vary a little bit, but I don't know of any major nerves that vary dramatically. I mean, I gotta be careful. Any nerve axons that vary dramatically. The nerve itself might vary because the median nerve is probably bigger here, and as some of the nerves axons go off and sense these muscles or control these muscles, it gets smaller, so it goes down. But the axons themselves, I believe, are roughly the same size. I'm not absolutely certain that they, about that, but I've never heard of axons varying their size dramatically as you go down. Yes.
Do we have to compensate for the nerves that run here for like calculating the speed, like the axon?
Well, you would if you really wanted to calculate the speed carefully. You'd have to solve the entire partial differential equation. But now, with Hodgkin-Huxley model here and sort of a passive nerve axon here, all coupled, it'd be a complicated thing. And you get roughly the same idea that myelinated nerves are proportional to their speed, but you get it more accurately. So a lot of hand waving here I've done. You could do it in a very more rigorous way, and people have. One thing we haven't talked about much is how the nerve signals get from either the nerve to the muscle or from a nerve to another nerve. And one reason is that there's a lot of chemistry involved in that. There's chemical synapses where the signal crosses. I'm just going to leave that for the physiology class. It's not as much a physics problem. There's a little bit of physics. We talked about diffusion of neurotransmitters, but mostly it's a biochemistry problem that we'll skip. Yes?
So for the squid, why do they have such big axons, 1 millimeter diameter axons? We see in the graph that unmyelinated axons are not as good when they get up to a certain radius.
I'll tell you what I think is myelination developed somewhere on the evolutionary tree, and the squids branched off before it was developed. So they didn't have that option. So either they'd have to independently develop myelination, which apparently they didn't do, or they just make their axons bigger. And so any animal that doesn't have the option of myelination and doesn't develop it independently can only make big axons. So people sometimes use lobsters. The tail flip reflex in the lobster has great big axons. People even look at earthworms. Earthworms have great big axons that control kind of when they shrink down. They didn't have the option of myelination.
Do you know which one's faster, though, like a myelinated squid or like human myelinated?
Well, I would assume that if such a thing as myelinated squid existed, it would be ultra fast. But I don't know of any really large myelinated axons. About the biggest axons in the humans are on the order of maybe 20 microns diameter, I think, myelinated. And why people don't have even bigger myelinated axons? I assume it's because they end up taking a lot of space, but you could argue there might be some really important thing, your trigger finger for your gun or something. I mean, when you evolved, it's hard to say. If you had one really important motion, like the squid and its escape reflex, and you had myelination, you could imagine evolving a great big myelinated axon to do it. But I can't think of any case in animal where that has happened. Okay, so the last thing I want to do is I want to talk a little bit about equations you need to know for the exam. So let's get down to some nitty-gritty. Okay, the exam consists of basically chapters 4, 5, and 6. So chapter 4, we talked about 3 things. First of all, we talked about heat conduction, which is really kind of a homework problem in chapter 4. It kind of goes back to almost for chapter 3. The heat conduction, we had an equation for the temperature. The derivative of the rate of change of the temperature is equal to a diffusion constant times the second derivative of space for the temperature, and we usually include a source term that's in metabolism, plus, and we can write it as the specific metabolic rate over the specific heat capacity. And that is essentially the diffusion equation, which is also known as the heat equation, just for conduction. If you wanted radiation or convection or things, you'd have to add in other terms, but that's not covered on this exam. And you should also remember that in the derivation we used J was the amount of thermal energy per unit area per unit time, a current density, and that was minus the kappa, which was the thermal conductivity, times dT dx. So I call this one equation, but technically you ought to remember what the J was that used in this derivation. And then we had diffusion. And diffusion is almost the same thing, you just change the name of the variables. You have some concentration. And how does it change with time? A diffusion constant times C, second derivative. And if you had a source, you'd add another term, but if you have things that aren't created or destroyed, all you get is these 2 equations. And your J is just minus the diffusion constant dC dx. So these are 2 equations, but really they're one equation. It's just you've renamed the variables in one case. And you also, a result from one-dimensional diffusion, we found that typical distance that something diffuses goes as 2dt square root time, diffusion constant to time. And this was important. This said that diffusion isn't linearly proportional to time like a speed. Diffusion grows as square root of time. And that means that you get a lot of diffusion acts very quickly over small distances. If you solve this for t, diffusion gets very rapid over small distances, but it gets slower over big distances. And we use this for various examples in your homework. Diffusion across the neuromuscular synapse, diffusion of air, why breathe. We saw this several times. So you remember that result. And the way to remember it is that the units of the diffusion constant are meters squared per second. So if you multiply by a second and then take the square root, you get something with meters. So if you just use the units, it can help you remember the equations. The only thing hard to remember is the 2. That is chapter 4, equations. 3 for chapter 4. Chapter 5 was not the longest chapter. We talked about osmotic pressure. And we came up with the osmotic pressure equation. The osmotic pressure, pi, is concentration RT. Now the good news is, this is really the ideal gas law. P times V, which we moved to the other side to make it a concentration, PV equals nRT, or PV equals n number of molecules times Boltzmann's constant T, depending on whether you want to use moles or molecules. It's all the same thing. So this allows you to calculate osmotic pressure. You should remember what osmotic pressure was. It's the only equation from chapter 5 you have to really memorize. Okay. Chapter 6 had 2 equations I want you to remember. First of all, the Nernst potential. Proved to play a crucial role in the Hodgkin-Huxley model. So for any ion channel, ions, the Nernst potential is Boltzmann's constant temperature over the charge times the log of the concentration ratio. Whatever the variable is, external divided by internal. That's where diffusion and electric forces are in balance. So if you have a lot of sodium on the outside and not much on the inside, like in the nerve axon, this becomes a positive number. You get a positive Nernst potential. If you have a lot of potassium on the inside, but not much, this is a number less than 1. Log of something less than 1 is negative, and you get a negative Nernst potential. So we did this, and you have one in your homework. And the other thing is the cable equation, which is lambda squared d squared v dx squared equals tau dv dt plus v. Those are for chapter 6. And you might think, well, that's a whole nother equation, but really, it's almost the same as the diffusion equation. It's just got this extra term. So 3 of these 6 equations have second derivative in space, single derivative in time, the diffusion equation. And I guess the thing you ought to remember is J for these is minus sigma dv dx. So I guess you could say really it's 9 equations. I view these as intermediate steps in the derivation of these equations, but you should remember them. These all have exactly the same form. A current density is some constant times a gradient of some variable. And that are the equations you have to know and memorize, basically. There's other things on the exam that we talked about that can be on the exam, but I would give you any equations you needed. For instance, we talked about diffusion and convection together, and that involved the Peclet number. And the Peclet number was the convective J versus the diffusive J. I didn't ask you to remember the convective J, so I'd have to give it to you, but you ought to at least remember that diffusion and convection can act together and give you some funny results. We talked a little bit about the artificial kidney and how you can do dialysis. You don't have to memorize any of the equations, but if I gave you a problem, you have to be able to calculate a time constant for dialysis or something like that. We talked a little bit about countercurrent transport, where you have flow going one way here and flow going another way here, and they could trade heat or ions or whatever it was, and we found the equations for countercurrent, and we analyzed them, and we found it can often be a useful way to transport molecules. So you have to be familiar with countercurrent equations, but again, you don't have to memorize the equations. We spent a lot of time talking about the Hodgkin-Huxley model with that great big m cubed h and n to the fourth business. You need to know that, but you don't need to memorize those equations. And we talked about the voltage clamp, which is how Hodgkin-Huxley got their data. You need to know what the voltage clamp is. And we talked today about propagation of axons and about myelinated nerve axons. You need to know that material. So that is some of the material that you need to know. I can't say that it's every bit of it, but I tried to summarize the vast majority of it. And if you look into practice exams, which I sent out to you all, so you should have them, you'll find that those are most of the topics, and I tried to make the practice exams consistent with what I just described as the topics. You don't have to memorize a bunch of constants. You don't have to memorize what D is for various molecules, or what the value of Boltzmann's constant or the charge of an electron. Those kind of things don't be given, either at the top of the exam or in problems. You don't have to memorize a bunch of constants. Otherwise, the exam's going to be a lot like the same format as the first exam for multiple choice, or not multiple choice, for a short answer, yes or no, 3 problems, and 1 little essay at the end. Any questions on sort of what's going to expect for the exam too? Okay, now you have the practice exams. I suggest you try to look at them. We will spend literally the next 2 classes going over them and answering your questions that you have, and you'll have homework due at the end of class. I should be able to get that graded and back to you on Monday, so you'll have it to study for the exam. So, yes?
Nothing.
This is out of the way. Okay. So otherwise, I will see you Friday, and we'll review.